And so, Bobby, the floor is yours. I'll just give a quick bio of Bobby. So Bobby Levine is the CEO of Digested Organics, a Michigan-based company that specializes in advanced filtration solutions for wastewater treatment and water reclamation. Bobby founded the company 10 years ago and recently oversaw its merger with the Mott Corporation, a global leader of specialty filtration solutions. Bobby completed his PhD in chemical engineering at the University of Michigan, and prior to Digested Organics, co-founded and sold a company that developed algae-based immune support ingredients for animal feeds and human nutrition. So with that, Bobby, the floor is yours.
Great. Thanks, Paul. Really appreciate it. And thanks, everyone, for tuning in and hearing about digestate treatment. I will start just with a little background on Digested Organics, so you know where we're coming from, and then briefly some of the benefits and reasons why we're even talking about digestate management. I'll take you through two of our projects that kind of highlight technologies that we use for digestate treatment, talk about where the nutrients end up, and then also look at our fertilizer products, which we brand under our TerraFlow Organics brand name. So our vision and really our mission is to upcycle liquid organic wastes into clean water and value-added products, particularly when we talk about digestate, which is usually on the order of 97% water, 3% nutrients. There's a lot of water there to reclaim in certain areas. That means more than others, but those products also can mean a lot in terms of revenue generation and added environmental benefits. So we do this both for digestate as well as a slew of other waste streams throughout various industries. As a company, we are a full-service engineering and manufacturing firm. So we're based in Michigan. We engineer, design, and then make filtration systems to tackle lots of different waste streams. Today we'll be talking about digestate. And I just want to highlight that we do that in a project management environment. So every project gets a unique project manager that is dedicated to it and looks at all of the unique aspects of that project and what that means both for our customer, which tends to be a developer or an EPC, as well as their customer, which is the farms, the community, et cetera. So really looking to provide holistic digestate treatment solutions. Here's a couple of pictures of our shop. We're about a 20,000 square foot facility in Plymouth, Michigan, just outside of Detroit. As a company, we're about 50 individuals in our unit, and then we merged with the Mott Corporation, which is a larger company based in Connecticut, about 60 years of specialty experience with gas filtration. And so pairing both of our companies together would really offer a full suite of services, both in the liquid side also. So what we're going to talk about today is really how our platforms can convert digestate into value-added resources and increase profitability in your projects. And it really is in some cases a closed loop where we're taking this manure that's been digested, going through a solution, typically a filtration based, but also sometimes with evaporation and other technologies added on, getting that clean water and that organic fertilizer, and that in some cases is in a loop, right back to that animal. Whether that's water for animal drinking water or fertilizer to grow crops that animal will eat. So really trying to holistically address what a lot of these biogas projects are facing when it comes to nutrient management. A couple of the benefits and really the reason why you would do digestate treatment and not just land apply the digestate, I break it into financial, environmental, and social benefits. I just want to highlight on a couple of these because Paul already mentioned this. Obviously, there's reduced hauling and spreading costs. But something that fewer people know about is that if we actually treat the digestate and remove volatile solids from it, we can improve a project's CI score because the model assumes a certain amount of leftover organics that our our lagoons sort of stored and still release methane. So we've actually quantified that and can help customers evaluate the impact of that. Obviously, if you can sell fertilizer, that's a huge value add to a project that might not have had that before. I think we're also seeing a change in mindset where if you can tell the feedstock providers that you can reduce volume, so if a farmer gives you 100 gallons of manure and you only give them back 50 gallons of digestate, they're willing to pay for that in essence. And that can be a big part of the economics of how a project was run. And then there's also new water and nutrient trading credits, which in certain areas will allow you to, again, get some financial benefit from that. Environmentally, I think these are pretty obvious. We are able to reduce excess nutrient loading if we are applying concentrated fertilizers instead of dilute digestate. We can do it in a more targeted way to increase crop yields. So farmers are not facing a full lagoon where they have to land apply, maybe in the winter or some other time where it's just not ideal for crop uptake. And then socially, I think as some of these projects get larger, it's really important to think about the community aspect. There's almost not a single project that doesn't have some negative article about, some community meeting, too many trucks on the road, new odors. This is a way to show that you're taking the community seriously around, especially on these hub and spoke projects, around the transportation of feedstock in and out, and how we can improve the overall outcome for all the participants in a project. There are kind of four main types of digesters that we're working with today: dairy, swine, poultry, and food waste. I think each of them have some unique characteristics I'll just want to highlight. So when you think about some of the solutions we offer in the projects you're running, you can think about what makes the most sense for you. So dairy, some of it tends to be pretty dilute, so it's costly to haul and spread. But when we look at the two case studies I'm going to show you, one makes a liquid concentrate that has almost all the phosphorus in it, and the other makes a solid concentrate. And some sites are set up to handle solids, and some are not. Some just have lagoons. And so that's sort of a major consideration when we think about spreading throughout the year. In swine, we see a lot of large covered lagoons that get cold in the wintertime and don't produce gas. But if we want to process digestate year round, how do we do that in a way that preserves those volatile solids so that the gas revenues don't suffer? We have a solution for that. And then we also see that they're facing nitrification and denitrification costs from existing treatment programs that we can overhaul and actually use the nitrogen to make a fertilizer instead of just paying a bunch of money to put it into the air. Poultry and to some extent food waste are unique in that they tend to come in with a really dry feedstock. So some of this poultry manure or litter can be 40–50% dry matter that requires dilution. And so we can help by you're adding a liquid. You're going through the digestion process, you need to pull that liquid back out, typically remove the ammonia and reuse the liquid because you can't afford to dump in fresh water and then haul away digestate. So, and that, again, sometimes with food waste can come in pretty high solids as well. So something to think about in each of these types of feedstocks and something that we have solution sets for. This is the entire slew of equipment and unit operations that we provide. We're not going to go through this in detail. Instead, we're going to focus on two main case studies that highlight several of these technologies and how we put them together to treat digestate. So the first technology platform I want to talk about is it's sort of what I call our all liquid platform. Basically, all of the concentrates of the nutrients are in a liquid form. We're not making a stackable solid anywhere. So this is our BC Organics project in Greenleaf, Wisconsin. Dynamic is the owner of this project. And it is designed for 720,000 gallons per day of pressate. So they're digesting dairy manure. They are screw pressing. And then we get the liquid pressate from the screw press. And we are designed for 50% recovery as clean water back to the farms or to be river discharged. And the technologies we're using to do that are a stainless steel ultrafiltration system, which is a tubular membrane, superfiltration, which is a tight ultrafilter, very fouling resistant chemistry, and then a unique process for reverse osmosis that is, we call it sub-induction time reverse osmosis, but it's a sequencing batch style process to help boost recovery and lower energy costs. And then we polish that water with biofiltration. So the key, this whole platform, again, was designed to keep all the concentrates liquid, was designed so that everything could be pumpable and easy to move back and forth to the farm. And then was really targeting volume reduction for these farms. So I have pictures, but I also thought if this video will play, we could just see the equipment as it is at the farm. We'll sort of narrate here as we go, but this is the facility. It has 16 large digester tanks that are 1.3 million gallons each, processing, close to 1 million gallons per day of the raw manure coming in. This building here in the floor is where the water treatment equipment is. They're using burger presses to create liquid pressate and then around 135 tons of fiber per day. This is just upstream of our process. This is pretty common to create a bedding product. They're actually then running that bedding product through rotary dryers to create a sellable bedding product for nearby farms to purchase. And then there's some excess product that is also produced. So this is our facility called the Nutrient Concentration and Water Reclamation System, again, comprised of these multiple filtration unit operations. This is looking here at the ultrafilter, the main first step in the process that is taking the pressate and removing suspended solids, which is principally all of the phosphorus. So the first step here on the way to the ultrafilter is actually some grit removal. This is just to help remove sand and abrasive particles before going to the filters. This is a non-powered like hydrocyclone approach. These are the stainless steel ultrafilters. Again, we're seeing 90+% phosphorus and organic nitrogen removal in these, producing a clear amber colored permeate. This is a picture of what the permeate looks like. And again, so there's this, it's transparent. You can see through it, and we've removed all the pathogens in the phosphorus. This is what the superfiltration looks like. So these are spiral wound membranes. And again, they're doing a tighter cut. So it's sort of like a second stage of ultrafiltration, but with a very tight ultrafilter membrane to get lighter colored permeate that'll then go to the reverse osmosis system. So this is the high pressure reverse osmosis system. So it's actually two ROs in the project. The first is high pressure. This is concentrating all of the ammonia and the potassium into a concentrate, a liquid concentrate, and then making clean water, which you can see here. And then that clean water is put through a polishing RO at low pressure to just do a final polish that's another 90+% removal of various contaminants, including ammonia, to make our clean water product. And then as a final step on the way to the river, they go through biofiltration towers. These are packed with a small plastic media that bugs are growing on that can nitrify the ammonia, remove any trace amounts of organic matter left, and then send that water nicely aerated through our ultraviolet disinfection system and out to the river or back to the farms for reuse. They have need of it for irrigation, like in warmer months. And then here is a goofy video of me drinking the water on my last trip there. We have a Green Bay Packers tap for anyone who's interested. Actually tastes pretty good. And then these are just the kind of a shot of the materials as it's going. So you can see it starts with the digested pressate on the left and gets clearer as it goes. All right. So I'll zoom through these pictures just so when you see it online, you'll have access to some of the pictures instead of the video. But that video is up on YouTube as well. So another picture here, I'll give you a little bit of insight into how the project is running. We are regularly producing water. We are discharging to the East River under an NPDES permit. So we worked closely with Dynamic to help them get that permit. And that's working really well. And so is sending that water back to some of the local participating farms. And then the concentrates are collected, and some of the farms are piped back, some are trucked back to the farm. This is a picture of our operator and an employee from Dynamic actually witnessing the river discharge where it falls into the East River. Some of the learnings I think I want to highlight for people here that we've seen bringing online this large plant, really the largest that we're aware of that filters digestate at this scale, is that there's lots going on in our project, both with different unit operations as well as upstream. So how are the screw presses running? How is the dryer running? If the dryer goes down for 2 hours, then we have to shut off the screw presses, and then we don't get pressate. So I think we are learning about how to balance those different operations with potential upstream upsets, and where would we have rather had bigger tankage to allow for continuous operations while there's upsets, and things like that. We have probably smaller tanks than we want between different buildings and different operations, and I think that's something that we'll take to future projects, just to think about for you when you plan your operations, when you have lots of steps dependent on each other. Something else I'll mention is temperature management. So our NPDES discharge permit requires certain temperatures for every month. And interestingly, in the winter time, as many of you know, the digestate is right around 100 degrees Fahrenheit, loses a little bit of temperature on its way to our building. We add a little bit of heat to it as we filter it. We actually need to chill that clean water before it hits the river because it is too hot. Our water's coming out warmer than the discharge permit allows for. So obviously there's lots of ways to do that, whether it's geothermal or air-cooled chillers or things like that, but it was a requirement sort of outside of our scope. It's something that we had worked with Dynamic on that we didn't realize was going to be as much of a problem as it is. So we are still working on the most cost-effective way to chill this large quantity of volume to get that to the river under the specifications of our permit, and having really productive conversations both with Dynamic, with the regulators, on how to make that work, and we've got some good solutions for that. But something that's just sort of we'll take forward to future projects. The final 2 points. One is on the biofilter. We are a fully mechanical process, right? Up until the biofilter, and then we're relying on those bugs to grow and to do their job. And they are doing that, but we had one instance, just as an example, where an operator accidentally left a pump on, probably very negatively impacted the biology for a brief period of time in the towers, and it took time for that biology to come back, as it does in any biological wastewater treatment process. But that was different than one of our ultra filters, which is made out of stainless steel, and if it gets dirty, you clean it and it's back up and running in an hour. And so I think we had to plan a little bit better for that and understand the ramifications of human mistakes and redundancy and things like that. So a good learning for us as we paired that biological process at the end of the line with our mechanical filters. And then the other thing is staffing for 24/7 operations. Because we're discharging, we do need certified operators, and we need to understand when they're going to be available and not. And it's just a tough environment, I think, in lots of industries right now to hire good operators and to have enough of them to cover the operation. So that's something that we're working on with Dynamic. In terms of next steps, we're continuing to do a lot of work to optimize the process. I think there's lots of low-hanging fruit, whether it's turning down certain pumps to save electricity and without sacrificing throughput, or seeing if we can reduce cleaning frequency of certain membranes to get, again, same performance, lower cost. So we're doing a lot of that work in partnership with Dynamic now. And then as we'll talk about later, we're going to be looking at putting a fertilizer plant on this project to basically harness the RO concentrate and turn that into a sellable product. So it's a revenue stream that's now, again, sort of just left going back to the farms, but because there's such a premium on the organic fertilizer, per pound nitrogen, it makes tons of sense for us to capture that. All right, so our second project is also dairy manure, but this is like a solid platform where we're going to take the phosphorus, and instead of putting an ultra filter in this project, you'll see that we have a digester here on the left. We have a screw press, and we are going to a different piece of equipment that we call our solids removal and dewatering unit, or SRDU for short. And this is a unique technology. I'll show you some pictures in a minute, but we're trying to get most of the phosphorus into a stackable solid on a concrete pad. The liquid from that will go through similar filtration steps as you saw before. So we'll super filter, we'll do our high pressure RO, and then we're actually going to evaporate the RO concentrate, producing clean water, as well as an evaporator residue. And the key to this project, and the reason Bencourt Dairy came to us looking for a solution, is because they needed salts out of their manure. So they've been applying manure from tens of thousands of cows to land for a long time. There's too much salt to the point that crops will not grow well. And so this project was all about volume reduction and salt removal. And so basically all of the salts are now in this small volume of evaporated residues. We took 300,000 gallons per day of pressate coming out of the screw press up here. We turned it into 15,000 gallons per day of evaporated residue. which they can compost. They can apply to compost piles that they already have, or they can continue to evaporate naturally through evaporative lagoons. Or as you'll see, we can turn it into actually part of our sellable fertilizer product. So a very exciting project for us. This is actually being built right now. I don't have a lot of pictures, but I'll show you some pictures of the technologies. But we will be running this plant later this year. Very high water recovery here. So here we're at about 88% water recovery. So this platform, because it makes a solid product up front and it uses an evaporator at the end, we are much higher than the 50% recovery of the first platform. So water recovery is really important. This is interesting. And again, the benefits are really around volume reduction, salt removal, and then making a compostable high phosphorus product. So this is what the SRDU looks like. It's a unique system to get compressed air and very unique high molecular weight polymers into the digested pressate, flocculate it, float it, and then press it to make the cake and a clarified digestate. So we have a unique partnership with a company that makes the specialty polymer. We have this technical solution that involves these high efficiency mixing heads, which are sort of seen here at the top of this picture, and then a multi-disc press. And so we put these pieces together to create the SRDU, and it's been really successful for us in terms of getting very efficient separation of the solids. So this is dairy manure during a pilot in Wisconsin, actually. So you can see here, this is the flocculated floating solids. Again, this is containing most of the phosphorus, and then this is the clarified liquid. This is an example of what that cake looks like. Nice stackable cake, usually around 20% solids. This is a lot of data. What I'm trying to show here is concentration and what we remove in the SRDU. So if you just look at like total solids, total volatile solids, and phosphorus, this column shows you the pressate concentration, and this shows you the SRDU effluent, so that's the clarified liquid, and this is the wet cake. So again, if our pressate comes in at 4% solids, it probably leaves around 1.6% in the effluent and 20% in the cake. So that's the kind of concentration we're doing. And in terms of volatile solids, we're seeing about a 75% removal. And this goes back to that CI score I was talking about, where if your project today is just evaluated as digester plus screw press, or even digester plus centrifuge, we can use this technology to remove 75% of the volatile solids. And that will result in like a 10 to 20 point CI score bump, which we've had verified by third parties. So that's one interesting thing that this does. And then the second is remove about 84% of the phosphorus that is present in that pressate. So very high removal rate on phosphorus, also on organic nitrogen and suspended solids, and sets you up well for then downstream filtration. But if you're a project that all you need is phosphorus removal and you want a little CI score bump, bolting an SRDU onto what you're currently doing can be really advantageous. All right, so I want to end here in my last few minutes talking about fertilizers. There's a lot of excitement about fertilizers. Like Paul said, digestate contains nitrogen. Usually about 60 to 70% of that nitrogen is in the ammonia nitrogen form. That's why we're talking about ammonia. Interestingly, when that digestate sits in a lagoon for half a year before a farmer uses it, a lot of that ammonia is actually lost. Like it just goes into the air, it causes air pollution, doesn't do the farmer any good because it's gone. We want to capture that before it gets to that point. Obviously, this brings a new revenue source to the farm. And, if you look at the organic industry today, organic farmers really struggle to find cost-effective nitrogen that has high plant availability in year one. They're using a lot of pelleted products that are mixes of manures and composts and things. And they have nitrogen on the label, but that nitrogen isn't actually available for a long time, sometimes years. So it's just a very slow availability. We want to deliver plant available nitrogen out of the gate. And then finally, some of the organic sources today, not only are they expensive, they have regulatory limitations like Chilean nitrate, for example. And it complicates how growers can then distribute that product. Canada has different regulations than we do. So it'd be great to have new sources. So we saw this in about 2 years ago. We created TerraFlow Organics. So it's a wholly owned subsidiary. And our purpose here is to help create value from digestate by producing nitrogen-based fertilizer. So we have two kinds of products I want to talk about. The first are aqueous ammonia solutions. So if you're not familiar with fertilizers, they're usually labeled with their NP and K. So we have an 800 and a 1600 product. They look and handle identically. They look like water. They have no salts in them, but they are volatile, like Paul said. So we're at high pH, and they need to be treated the way a farmer would handle conventional aqueous ammonia. So that means it's tilled into the ground, it's diluted and distributed through drip tape. It's not center pivot irrigated into the air, for example. So it's nothing new for agriculture. Farmers have been dealing with ammonia, even anhydrous consideration that's sort of new to organics. And obviously both of these are only listed, so they are certified today for use and are sort of ready to go. So we've crossed that hurdle, and we've created the two concentrations so that buyers have options. Obviously, it's less expensive, per pound of nitrogen to move the 1600 than it is the 800, just because of the concentration. The other product I'm really excited about is our 605. This is what I call a concentrated digestate. So we have used our filtration systems to pull out water. We've used an evaporator to pull out more water, and now we're left with a 6% nitrogen product that also has quite a bit of potassium. It's usually actually a little bit more potassium than nitrogen. We label it 605. It often tests more like 606 or 607. It is it's a dark liquid. It has about 50% total solids, which is sometimes surprising to people, but it still has very low viscosity. So it still pumps like water, but those dissolved solids are partially the nitrogen, but partially, the potassium and all the other salts that were in the digestate. We make sure it's screened so it won't clog any kind of drip systems or nozzles, but it is pH stabilized, and that's the key. So it is between pH 5 and 6. We are not adding any unique additives like citric acid, but we have developed a process that allows us to stabilize it and keep it 100% plant available nitrogen. So this, again, for certain projects makes a lot of sense because it takes all of the nutrients that are in that RO concentrate and sells them. Whereas when we make the aqueous ammonia solutions, we're using a thermal distillation process, but we're leaving all the salts behind. So the project still has to manage essentially like a strict RO concentrate stream that contains the potassium, the sodium, and the other salts. And in certain cases, that's no problem. In other cases, it's not advantageous. So just something to think about when you think about which fertilizer makes the most sense. Here's just another picture kind of showing you what a dairy manure digestate looks like going through our process. One final thing I want to end on, if I just have one extra minute. A lot of developers are interested in these hub and spoke models, but they have dilute manure or they have manure that's really far away from the digesters. And so something I think we can also offer is a filtration solution that actually concentrates the volatile solids in the feedstock prior to digestion. This also does concentrate the phosphorus in the organic nitrogen. We use our ultrafiltration for this or our SRDU for this, but just wanted to say that that's another technology that we are offering the industry. We have some cool videos on YouTube. Paul's been great about putting those up for educational purposes, so definitely check that out. And if you have a project, we would love to talk to you about how we pilot. So we have a significant pilot program that involves either samples coming to us in Michigan or equipment coming to you wherever your project is. And it's a big part of how we get to start working with a client and then also show them with their exact digestate or their exact manure where nutrients partition and how best we can serve them with different technologies. So I will stop there and see if there are any questions.
Yeah, there are some, Bobby. Thank you. Nice job. So the concept about CI score improvement is getting some traction. And so I'll read this. Why would nutrient separation improve CI score by removal from digestate? If they're volatile, was the digestion process inefficient? How much would separation improve the CI score approximately?
Yeah, so typically what we've seen is that the standard model being used, the GREET model, assumes that the digester and the screw press, let's say, leave volatile solids in the digestate. The digestate's going to an anaerobic lagoon. Some of that is still resulting in methane and evolving into the atmosphere. If we remove more volatile solids than what is estimated in the model, we get a CI score improvement. Like I said, it's usually between 10 and 20 points, and it depends on the climate. So because more degradation happens in warmer climates, it's actually a bigger CI score improvement in warmer climates. But it has nothing to do with the nitrogen or the phosphorus. It just has to do with the ability to remove additional volatile solids after digestion through our processes, and then keeping those volatile solids aerobic. So if you do the SRDU, let's say, or the UF, you remove 80, 90+% of the volatile solids, you can't put those in an anaerobic situation. But if you do the SRDU, it's natural to compost that material or land apply that material, and then those volatile solids are not degrading anaerobically.
Thank you. So lots of questions coming in, but we're right on time. So we may need to be addressing some of these by email afterwards. So Paul at green-tech.com will get to me and I can distribute accordingly. But thank you, Bobby. You're doing some amazing work. So appreciate it. So next up.